Number 5, we are asked to use logarithmic differentiation to find the derivative of x cubed times e to the 2x divided by the 7th power of x minus 1 times sine cubed of x, which I've rewritten as the cube of sine of x. So in using logarithmic differentiation, the first thing we want to do is take the natural log of each side. So we get the natural log of y is equal to the natural log of all of these, of all of this. But I'm going to use rules of logarithms here and write this as the natural log of x cubed plus the natural log of e to the 2x minus the natural log of x minus 1 to the 7th power minus the natural log of sine of x to the 3rd power. And now, all of these, I'm going to work with this more. I'm going to bring the 3 up to the front, so this is 3 times the natural log of x. Here the natural log and the e undo one another, and we're left with just 2x. Then we'll have minus 7 times the natural log of x minus 1 minus 3 times the natural log of sine x. Now we differentiate each side with respect to x. Over here, since this is a function of y, that means we're going to get 1 over y times dy over dx. Here we're going to get 3 times the derivative of the natural log of x, which is 1 over x. The derivative of 2x is 2, minus 7 times the derivative of x minus 1, that's going to be 1 over x minus 1, times the derivative of x minus 1, which is 1, minus 3 times the 1 over sine of x times the derivative of cosine of sine of x, which is cosine of x. I'm going to clean this up just a little bit more before we do anything else. I'm going to call this 3 over x plus 2 minus 7 over x minus 1 minus 3 cotangent x. So now what we need to do is solve for dy dx by multiplying each side by y. Well, on the left side I'm going to multiply by y, and on the right side I'm going to multiply by this other expression we have for y. X cubed e to the 2x over x minus 1 to the 7th sine cubed of x. And I'll just get rid of the y and the 1 over y. Number 6. We are supposed to write this expression as a single logarithm. The first thing you're going to want to do is get rid of these coefficients in front of the logarithms. We're using one of the rules we've discussed in class. That's going to be the natural log of x cubed plus the natural log of y to the 1/2 minus the natural log of 3 squared. These two logarithms can be combined through multiplication. This is the natural log of x cubed times y to the 1/2. And then this is just the natural log of 9. These two logarithms can be combined through division. So we'll have x cubed times y to the 1/2, but I'm going to rewrite that y to the 1/2 as the square root of y, and then that's going to be divided by 9. Number 7, we're given two logarithms and we are asked to write them in expanded form. So I went ahead and rewrote the one in part A as the natural log of 25x to the 5th over y to the 1/3. So this is going to be equal to the natural log of 25 plus the natural log of x to the 5th minus the natural log of y to the 1/3. If you like, you can rewrite 25 as 5 squared. we'll rewrite natural log of x to the fifth as 5 times the natural log of x. And then here we'll write minus 1/3 times the natural log of y. And then we can rewrite this again as 2 natural log of 5 plus 5 natural log of x minus 1/3 natural log of y. In part B, we can recognize that x to the fourth minus 16 is a difference of 2 squares. And so it factors into x squared minus 4 and x squared plus 4. Now x squared minus 4 is also a difference of 2 squares, and it can be written as x plus 2 times x minus 2. Finally, we can use the rules of logarithms and write this as the natural log of x squared plus 4 plus the natural log of x plus 2 plus the natural log of x minus 2. I think this answer is maybe different from the one that I gave you in the solutions. I think I have a minus there when there should be a plus. Number 8. We are asked to evaluate the integral from -4 to 1 of f of x, where f of x is the function represented by the accompanying graph. So what I'm going to do is notice that the function is below the x-axis between -4 and 3, and then to the -4 and -3, and to the right of -3 the function is positive. So I'm going to split this up into the integral of f of x from -4 to -3 plus the integral from -3 to positive 1. Alright, so now since the function is below the x-axis between -4 and -3, what we're going to get when we evaluate this integral is a negative. In fact, it's -1 times the area of the region bounded by x equals -4 and x equals -3 below the x-axis but above the graph of f of x. That area is just 1/2, but remember we multiply it by -1, and so that's going to be -1/2. Now as for the integral of f of x from -3 to 1, in that case the function is above the x-axis. So the integral is going to be just the area between x equals -3 and x equals 1 below the graph of f of x but above the x-axis. And so it's just going to be that area, and we can count squares. And I believe there are 1, 2, 3, 4, 5, 6 of those squares. So we get -1/2 plus 6, that is 5.5 or 5.5. Number 9, we are supposed to state the domain and range of y equals the natural log of x. Well, the graph of the function looks something like this. The domain, remember, is the set of x values for which the function is defined. And so that would be from 0 to positive infinity. The range is the set of y values on the graph. Those go from -infinity to positive infinity. In number 10, we are asked to find the domain and range of the function y equals e to the x. Again, we'll look at the graph. It looks something like this. The domain is a set of x values. Well, there's a horizontal asymptote out here along the negative x-axis. The domain is going to be from -infinity to positive infinity. And the range is a set of y values on this graph. The graph never reaches 0, but it gets as close. It gets arbitrarily close. Number 11. We are supposed to evaluate these four limits. The first one is the limit as x tends to infinity of the natural log of x. We can look at the graph of the natural log of x, and we see that as x grows, so does the natural log of x. And it is unbounded above, so we can say that that limit is infinity. If we look at the limit as x tends to 0 from the right, we look at the graph and see what happens to y as we let x get closer to 0 from the right. The y values are headed to negative infinity. Part B, we've got the limit of e to the x as x tends to infinity. As x tends to infinity, the y's also tend to infinity. And in part D, we look at the limit of e to the x as x tends to negative infinity. And in that case, the y's tend to 0. Number 12. We are given this sum in sigma notation, and we're asked to write it in expanded notation. So what we are asked to do is write out the individual terms. So we're going to evaluate this expression, negative 1 to the I times I plus 1 over 3, at each of the values I equals 1, I equals 2, I equals 3, and I equals 4. When I equals 1, we get negative 1 to the first power, which is negative 1, times 1 plus 1 over 3, 2/3. When I equals 2, we get negative 1 squared, which is plus 1, times 2 plus 1 over 3. When I equals 3, we get negative 1 cubed, which is negative 1, times 3 plus 1 is 4, divided by 3. And then for I equals 4, we get negative 1 to the fourth power, that's positive 1, times 4 over 3. This simplifies to negative 2/3 plus 1 minus 4/3 I see I made a mistake. That should actually be 5/3 there. Minus 5/3 plus 5/3. Number 13. We are given this sum and are asked to write it in sigma notation. So what you want to do is determine a pattern in these 5 terms. Well, I am immediately drawn to the denominators. Those denominators all have a particular property. Each of those is a perfect square. So we can write this as 6 over 1 squared, plus 7 over 2 squared, plus 8 over 3 squared, plus 9 over 4 squared, plus 10 over 5 squared. So it looks like this term could correspond to I equals 1, this one to I equals 2, the third one to I equals 3, and so on. So it would be nice if we could write each of these numerators in terms of the particular value of I, the associated value of I. Well, we can subtract or separate I off of each one of those numerators in the following way. We could write 6 as 1 plus 5, that's over 1 squared. We could write 7 as 2 plus 5, over 2 squared. And then 3 plus 5, over 3 squared. 4 plus 5, over 4 squared. And 5 plus 5, over 5 squared. So now let's look for commonalities between the 5 terms and also differences. So what's common is this fraction. Well, you've got something plus 5 divided by something. Now this something in the numerator goes from 1 to 5, and then the denominator goes from 1 squared to 5 squared. So this could be written as the sum of I plus 5 over I squared. I starts at 1 and finishes at 5. I'm not saying that's the only solution, but that was the first one I saw.